Good afternoon, one and all present here. Today we are going to discuss about floating point operation. So floating point operation is nothing but by number which is represented with a decimal point in between. So it is represented in two types. One is single precision format and another one is double precision format. So in single precision format, the representation consists of sign bit, exponent bit and fraction, which is altogether consists of 32-bit representation, where the fractional part, which is also called as mantissa, will take 23 bits, the exponent field will take 8 bits and your sign bit will take 1 bit. So altogether it going to give you 32-bit representation. So in general, a single precision representation will be represented as -1 whole power s into fraction into 2 power exponent. So this is how we are going to represent a single precision format. Now we are going to discuss about double precision format. So double precision format is nothing but 232-bit format, which is nothing but 64-bit format. So here we are going to represent the fractional point with 56-bit representation and exponent with 11-bit representation, and once again sign bit with 1-bit representation. So all together which going to give you a 64-bit representation. So double precision format is the double time of the single precision format. So the general representation of double precision format is represented by -1 whole power s into 1 plus fraction into 2 power exponent. So this is the general representation in which how we are going to represent a double precision floating point number. Now we are going to discuss how to perform a floating point addition operation. So it consists of certain steps. Let us see the steps first, then we see with an example. So your first step is we have to check the difference between the exponents. So check the difference. Check the difference D between the two exponents E1 minus E2. The concept is we have to match the smaller exponent to the larger exponent. So what we have to do is shift the number with smaller exponent to the number to the right side to make it equal to the larger exponent. Next step, after performing this, we are going to add the significance. After performing the addition of the significance, we are going to normalize the resultant significant. So once the normalization is done, we are going to perform the round off operation. So round off of the result. So with this we are going to conclude our floating point addition. So now we are going to see this with the help of a problem. We are going to take an example of a 4-digit decimal number 9.999 into 10 power 1 plus 1.610 into 10 power minus 1. So as the rules, we see that both the exponents should match each other, only then we are going to perform the addition. So now here, which is the smaller exponent in the sense 10 power minus 1 is said to be the smaller exponent. So in order to match it to the larger exponent, what we are going to do is we are going to shift the point to the right side by 1 position, and we are going to check whether both the exponents are going to get matched. Now 0.161 into 10 power 0, as my point moved one side to the right, my position becomes 0. So still I didn't get match with my larger exponent. So once again I am going to place a 0 after the decimal point and I am going to add a number. Now it is going to become 10 power 1. Now both the exponents got matched. Now we are going to perform the addition of these two significants, that is the second step, add the significance. So our question is 9.999 into 10 power 1 along with 0.016 into 10 power 1. As in the given question, after the decimal point there are only 3 digits. We can also take up to 3 digits. So we can neglect the 1 and we can take up to 016. Now perform the addition. So 9 plus 6 going to gives you 15. So the carry 9 plus 1 10, 10 plus 1 11. So once again 9 plus 1 10, 0 here and the carry over here. So 9 plus 1 10. So this is the result of your significant. So now I have to check whether any overflow occurs. So in this no overflow occurs, so no issues. I have to still normalize my result. So normalization is nothing but I am going to place a number before the decimal point that should be a non-zero number, that should be a single number other than a non-zero number. That is, other than 0 we can place any non-zero number. So here I can convert it by shifting the point to one position right side. So we can convert it into 1.0015. As I am going to move the point to one position right, to the exponent I am going to add one value. So finally which is going to become 1 plus 1 2. So 1.0015. So this is my normalized answer, but still I have to round off my result. So I can round off my result. So this is the normalization. So after performing normalization, round off the result. This can be done by 1.00. I can make this 15 into 2 a whole number. So this is my final answer. So this is how I am going to perform a floating point addition operation. Now in this problem we got two numbers which is both belongs to a decimal type. Now for example, if we get another type of question, for example, perform binary addition. The question is binary addition, but the given number is to be of type decimal. So binary addition with 0.5 minus 0.4375. So in this we have to see the question carefully. If it is just a given addition, we can perform by using the previous step, but here the word binary addition was given, with which we cannot able to proceed as in the previous model. So what I have to do is, first I have to convert this given decimal number into the binary form. Later I have to perform the addition, and finally I have to proceed my result with the decimal representation. The one which I get in binary should get converted into decimal, and then I have to present my result. So how we can do this? If a number which is placed before the point, then for example, if it is a whole number like 2.5, here I can convert this 2 into a binary form which we know already as 10. But now here before the point I don't have a whole number. As it is 0, I have no issues. The 0 is going to be 0, with which number it's going to get multiplied. But after the decimal point I have a non-zero number which cannot be represented as such. So I need to convert it into a binary representation. How this can be done is, I can take the number after the decimal point, only the number which is placed after the decimal point. That is, I am going to take only 0.5. So in order to represent it in binary, what I have to do is, I have to multiply the number by 2. So 0.5 into 2, which going to give you 1.0. So after performing this multiplication, once again what I am going to do is, I am going to take this 0.0 alone, because we are going to convert the number into binary which is placed after the decimal point. So once again 0 into 2 is going to be 0. So further I cannot proceed, because even though I can proceed, I am going to get 0 only as my result. So I can stop with this, and now just I am going to take the numbers which is placed before the points. So my binary representation of 0.5 is going to be 0.10 into 2 power 0 initially. So what I have to do is, so this is the binary form of 0.5. So whereas just I can place a 0, dummy 0 here. Now this is not a normalized form. So in order to make it normalized, what I am going to do is, just I am going to advance the point by one position, which going to give me 1.0. So after the decimal points, generally we used to represent 3 bits. So I can take it as 1.000 into, as the point is moving beyond the number, my power gets subtracted by 1. So this is my final form. So I have converted one number into binary representation. Now I am going to take the another number, that is 0.4375 into binary form. So the number 0.4375 into 2. So when I am going to multiply this 4375 into 2, I am going to get 0.875 as my answer. So once again, in turn, what I am going to do is, I am going to take this 0.875 alone, which is taken as 0.875 once again into 2. So this going to give me the number 1.75. Again I am going to take this 0.75. So 0.75 into 2, which going to give me 1.5. So in turn, I am going to proceed this multiplication until I am going to get 0 on both sides. So 0.5 into 2, which going to give me 1.0. So again I am going to proceed with 0.0 into 2, which going to give me 0.0. Once I get 0 on both sides, I can stop my multiplication. So here it ends with. So later what I have to do is, I have to take all the numbers which is placed before the decimal point, and this is the binary representation of 4375, where I can represent it as 0 point. I have to take from the beginning. So 0, 111, 0 into 2 power 0 initially. So once I have to write the result which should match the previous exponent, as it is a floating point addition, what I have to do is, I can check which number will gives me, which conversion will gives me the previous, match the previous exponent value. That is, if I move my point to by this one position, I am going to get subtracted by 1. So what I am going to do is 0.1110 into 2 power minus 1. So where I got both my exponents get matched now, so I can stop with this. Now the binary representation, we are going to perform the addition of 1.000 into 2 power minus 1 plus 0.111 into 2 power minus 1. If suppose it is going to be a positive number, I can proceed my addition as such, but the thing is, the question, it was given as minus 0.4375. So it is actually a binary subtraction which cannot be done as such. So the rule to perform a binary subtraction is, the given number, the number which is going to be subtracted need to be get converted into 1's complement, and then we have to take 2's complement. Finally, the result of the 2's complement along with the number need to be get added, and that will be my final result. So what I am going to do now is, now I am going to convert this 0.4375, the binary representation of 0.4375, that is 0.110 into 2 power minus 1 into 1's complement, which gives me 1.000 into 2 power minus 1, which is the 1's complement representation. So once again, still I have to convert it into 2's complement, so that I am going to add a 1. So which is going to gives me 0 plus 1 is 1. So 0 as such. So 1.001 into 2 power minus 1. Now this is the converted answer. Now I am going to perform addition of this 1.001 and this 0.0110. So here we are going to perform the addition of this 0.0111 into 2 power minus 1 along with 1.001 into 2 power minus 1. Perform addition. So which going to give me 1 plus 1 0 1, 1 plus 1 0 1, 1 plus 1 0 1 and 0 plus 1 1. So this is my final answer 0.1000. So this is the answer of my final result. So once again what I have to do is I have to perform the decimal conversion because the question was given in decimal form. So I have to represent the final answer also in the decimal form. So in order to convert it into decimal form, what I have to do is convert this binary number with respect to the decimal number, decimal number to binary number. So the binary representation can be written as 0.0001 into I am going to multiply this number 1 into, so still one more step, so 0.100, so still what I am going to do is I have to perform the normalization. So as it is a binary subtraction, what I am going to do is I cannot represent it as such because still my result is yet not get normalized. So what I am going to do is 0.100 which going to give me into 2 power minus 4. So this will be my final answer. So after this 0.100 into 2 power minus 4, what I am going to do is just I am going to convert it into the respective binary form. So which going to give me into 2 power 16 in the sense which will gives me 0.0675. So the respective addition of 0.5 and minus 0.4375 going to give me the answer 0.0675. So this is how we are going to perform the floating point addition. So now we are going to discuss about floating point multiplication. So the rule in floating point multiplication is going to be here. We are not going to see the exponent because different exponent we are going to perform the addition of the exponent. So what we are going to do is we are going to take two different numbers and we are going to perform the addition of the exponent, that is E1 plus E2. After addition of these two exponents, we are going to get a final answer, which we are going to perform the addition of the resultant significand. Later performing normal multiplication, we can represent the sum of these two exponents. Now we are going to discuss about floating point multiplication. So in floating point multiplication, which is somewhat similar to floating point addition, the only change in multiplication is, so in floating point addition what we did is, initially we need to match the two exponents, that is the number with smaller exponent is need to be converted to the number with larger exponent. But as it is in multiplication, we are not going to mind about the exponent conversion, whereas here what we are going to do is, here just we are going to add the exponents. So the exponents can be added, and after the addition of exponents, finally the significants are going to get multiplied. So once the significants are going to get multiplied, the resultant significant is going to be our answer, which need to be converted into the normalized form. So normalized form is nothing but, as I told you already, so before the decimal point we have to place a single digit non-zero number, that is other than 0, it can be any number from 1 to 9. So we have to convert our result into a normalized form. So after converting into the normalized form, we need to check for the overflow or underflow. If any overflow or underflow is there, we have to convert it into the another larger form, that is the larger exponent form. That is either if single precision, if overflow occurs, we can need to convert it into the double precision form. So later what we have to do is, we have to check for the rounded resultant. So if my result is already in the rounded form, so no problem, I can leave it as such. If not, what I have to do is, I have to convert it into the nearest round off form. So with that, we are going to conclude our multiplication. So now we are going to see how we can going to do this with the help of a problem. So this is the question given over here. This is a multiplication of floating point representation with a binary number. So my question is 1.000 into 2 power minus 1, which is going to be multiplied in turn with a negative binary number, that is minus 1.110 into 2 power minus 2. So if I check here, both the exponents consist of different numbers. So here it is the number minus 1, and once again here it is the number minus 2. So as I told you, the first step, I need to perform the addition of the exponents. So what I am going to do is, first I am going to add the exponents. So the first exponent, I have to take it along with the sign, only then I can able to get a proper answer. So minus 1, and the second exponent also going to proceed with a negative number. So minus, so once again minus 1 minus 2 going to give me minus 3. As it is a single precision format, my biased value for a single precision format is 127, and my biased value for a double precision format is 1023. So here it is only a single precision format, so I have to add the biased value along with the exponent. So minus 3 plus 127. So up to this I have completed my addition of two exponents. After performing this, I can able to perform the multiplication of significance. Significant is nothing but the fractional part. So normal multiplication, which we used to do regularly. So 1.000 into 1.110. So perform normal multiplication, which going to give me the result 1.110. Okay, so this is my final result, and I have to write it along with the exponent. Okay, so 2 power minus 3. So I have to look, now I have completed multiplication, I have completed my addition of exponents, I have performed the multiplication of two significants, and now I have to check for the normalization of my result. I have to check with the number. Already my result was expressed in the normalized form, so we need not to normalize it once again, so leave it as such. Next, after performing normalization, what I need to do is I have to check for whether it is in the proper rounded form. Okay, so if it is not in the proper rounded form, what I have to do is I have to renormalize if necessary occurs. If not, if it is already in the rounded form, what I can do is I can proceed as it is. So now my result 1.110 into 2 power minus 3 is already in a rounded form. That is only 3 points after the decimal point, no other points. So I don't have the necessity to perform the rounded off application. So I am going to write here just no change. So after performing this, I have to determine the sign of my answer. So here it is going to be a negative number. So my number is going to be a negative number. So this is how we are going to perform the floating point multiplication. Thank you.